Okay, this video I'll continue with you the AC circuits, and we'll take a few examples on how we apply the same theorems on AC. Okay, we finished the last video about the complex power. Now applying uh, theorems to AC. Okay, what we have: source conversion. So in source conversion, you have plus minus E with in series with an impedance Z. This is A and B. We can transform this back to a current source I in parallel with the same impedance Z. Okay, this is A, B, and here A, B. So I equal E to the Z. Okay, so it's exactly the same as in DC, except here we use what? We use complex numbers. Okay, so that's the source conversion. 1. 2. Thevenin's and Norton's. Thevenin's and Norton's. Any circuit, AC circuit, okay, can be, and we have 2 points A and B. We can obtain Thevenin's equivalent, E Thevenin's, in series with Z Thevenin's. Okay, AB, or Norton's current IN in parallel with Zn, and we have same points A and B. So this is Thevenin's equivalent circuit, and this is Norton's equivalent circuit. Okay, so E Thevenin's, same as in DC, Thevenin's voltage of Z Thevenin's impedance, I Norton and Norton current, and Zn equal Norton's impedance, and Zn is equal Z Thevenin's. Okay, E Thevenin's equal E open circuit voltage. Okay, E open circuit means that this is the circuit here, and this is A, and this is B, and plus minus E open circuit. Okay, IN equal short circuit current. Okay, so I short circuit. So if you have the circuit like this is A and B, we make a short circuit and we calculate what is I short circuit. Okay, so this is basically how we obtain IN and E Thevenin's. IN is the short circuit, E Thevenin's is the open circuit. How we obtain this is A and B, If we look at this here, we obtain Z Thevenin's equals Z Norton. Okay? Circuit with all sources removed. Exactly same as in DC. Removing a voltage source, we make a short circuit. Removing a current source, we make an open circuit, okay? And then we have superposition theorem. In superposition theorem, we make circuits exactly the same. For example, here you have E1, and here probably Z1, and then here you have Z2, and you may have here I2 current source. Then we have how many sources? We have two sources, okay? I1, let's say I1 here. We have a voltage source E1 and a current source E1. So by superposition, it means we'll be having two different circuits, one containing, this is Z1, this is Z2, and the current voltage source E1 plus minus E1, and here an open circuit because it's a current source, and then we have the current source here, I1, same here, Z2 and Z1, and we have a short circuit here, okay? So we have two circuits. In the first circuit we have we keep the source number 1 and remove source number 2, which is I1. It's the current source, so we make it open. In the second circuit, we keep the current source and remove the voltage source, which is E1. A voltage source, when we remove it, we make it a short circuit. So suppose that we want to find what is I1. So here is I1 bar, and here is I1 double bar. Then find I1 bar from the first circuit, find I1 double bar from the second circuit, then finally we say I1 equal I1 bar plus I1 double bar. Okay, that's basically the theorems. We apply them to AC exactly the same as we did in DC, except here we use what? We use complex numbers, okay? I want you to go through the examples. We have examples in the notes. It's very obvious, demonstrated very well, so you read them. I don't need to give you examples here in this video, but show you how you utilize these theorems, okay? Then we move to methods of analysis. Methods of analysis. Basically, we have two methods. One is mesh analysis, two is nodal analysis. Exactly the same as in DC. Except here we use impedances and admittances. In DC we use resistors, okay? So if we go to, look at mesh analysis, okay? In mesh analysis, we have loop currents. Assume that we have E1 here, Z1 here, Z2 here, E2 here, and you may have, let's say, an impedance here, Z3, okay? If we look at this circuit, we have two loop currents. Say this is loop I1 and this is loop I2. Okay, let's assume that we want to find using mesh analysis determine the current in Z1 or in Z2, let's say in Z2. Okay, the current in Z2, IZ2, equal I1 minus I2. Why? Because I1 in this direction, I2 in this direction here, and this is IZ2. Okay? So in the impedance Z2, we have two currents, I1 and I2, and they are in opposite directions, so we subtract them, which means that we have to find what is I1 and I2. We go to loop I1 and write the equation, same as in DC. For current I1, we add, there in the DC we added resistors, here we add impedances, Z1 plus Z2, okay? Have Z1 and Z2, okay? Times I1 minus Z2 times I2, okay? Equal the sum of all voltages. This is plus minus, this is plus minus, so it is E1 minus E2. So this is equation 1. Then we go to loop I2. We have minus Z2 I2, I1 plus, we have Z2 and Z3, Z2 plus Z3, I2 equal to, we have only E2 equal E2. So this is equation 2. So solve 1 and 2 to determine I1 and I2. And then we have IZ2 equal I1 minus I2. Okay? Now, assume that we know now I1 and we know I2. Okay? Let's draw it again. Here we have Z1. Here we have Z2. And here we have Z3. This is our original circuit. What we have here, plus minus E1. What we have here, plus minus 8. Okay? Now assume, and we have determined I1 and I2. What is the complex power supplied by each source? We want to determine the complex power supplied by each source. We have two sources. This is E1. This gives I1. Let's say I source 1. It supplies this one, which is equal E1 I S1 I S1 conjugate, okay? And I S1 equal I1. Okay, so we can calculate the complex power supplied by E1. The complex power supplied by E2, we have, this is E2, this is E2, and this is I is 2. Okay, so we have S2 here is equal E2 times I is 2. Conjugate. If we looked at I is 2, what is I is 2? This is I is 2 here. I is 2, and here is I is 1. So I is 1 and I1 are the same, but I is 2 is equal I2 minus I1. So I is 2 here because you have I2 here and you have I1 here. So I is 2 is equal I2 minus I. Okay? And you put it here. So we can determine the power or complex power supplied by each source. Okay? Same if we apply to nodal analysis. In nodal analysis, what we use in nodal analysis, use admittances instead of impedances. Let's assume that we have something like here, Z1, Z2. And we have Z3, ground here. We have Z4 and the ground. And let's say we have here, so Z6, Z5, and the ground. So assume here we have a current source, I1, a current source, I2, and a current source here, I3. Okay? Now, how many nodes we have? We have 3 nodes. This is node 1, say V1. This is node 2, V2. This is node 3, V3. So, to write nodal equations, say node 1, node V1, 1 over Z1 plus 1 over Z5, this is times V1. Then we say minus Z1, 1 over Z1 times V2, minus nothing connected between, let's assume that we have here Z6 connected like this. Okay, this is Z6 minus 1 over Z6 V3. Okay? Because Z6 is connected to V3. Then this is equal I1. This is equation. Okay, exactly the same as in DC, but here 1 over Z. 1 over Z1 is equal to I1, and so on. Okay? When we go to node 2, node V2, node V2 is connected to V1 through Z1, so we have minus 1 over Z1. عليكم السلام. هلا خليل شو أخبارك؟ Plus, now we have Z1 and Z2 and Z4, so 1 divided by Z1 plus 1 divided by Z2 plus 1 divided by Z4, okay, times V2. So this is the voltage V2. And now it's connected to V3 through Z2. So minus 1 over Z2 V3 is equal I2. Okay? Now we go to node V3. Okay? Node V3, what we have is connected to V1 through Z6. So we say minus 1 over Z6 V1 minus 1 over, connected to V2, to node 2, so Z2, so 1 over Z2 V2 plus, we have Z2, Z6, and Z3, okay? Z2, Z3, and Z6, so 1 over Z2 plus 1 over Z3 plus 1 over Z6 times V3 is equal to I3, and this is equation 3, and this is equation 2. We look at it, okay? We will go, and here for node V1, we forget to add Z6 because this is all the impedance is connected to node 1, Z1, Z5, and Z6. So here plus also 1 over Z6, okay? Here. Okay? So we solve 1, 2, and 3 to determine V1 and V2 and V3. This basically. So I want you to go and read the notes and the examples on this one, but keep in mind also always S equal V I absolute, okay? S as a vector, okay, is V I conjugate as a vector. It's important to understand that whether this is a voltage source, if it is, this is A, and it supplies I, what is S here? S is equal to A times I conjugate, and it will go P plus JQ, okay? So, if P equal positive, then E supplies active power, okay? If P is negative, then E delivers, absorbs, we say, it's not delivers. Supplies means delivers, we say absorbs. Then E absorbs active power. Same for Q. If Q is positive, same for Q. If Q is positive, then E supplies reactive power, okay? If Q is negative, then E absorbs negative, then E absorbs reactive power, okay? The same we apply for current sources. So if we want to determine the complex power supplied by a current source, and this is the current source, I, we have to determine what is the voltage plus minus E, okay, of V, the current source. Let's say this is V between A and B, or VAB, okay? This is the same point A, and this is some point B. So what is S? So S is equal complex power supplied by the current source. So the current source supply power to the system. How we determine it? Simply S equal V AB times I conjugate. Okay? Usually we know I, so we know I conjugate, and we need to determine what is voltage. And this is again will be P plus JQ. Okay? If P is positive, then current source supplies. Okay? If P is same for Q, okay? If P is negative, then the current source absorbs active power. Okay? Same for Q. So it's basically, if we determine the complex power supplied by a current source or a voltage source, we take the output from this current source, I, the current which is going out from the current source or the voltage source, and we multiply it by V. We take the conjugate of that, multiply it by V, will give us S supplied. So if P or Q are positive, it means this power or the active power are going out from the source to the system. It means supplied. But if it turns to be negative, it means coming from the system to the source. So it means that the source takes power or the active power from the system. Okay? I will keep up to this point here. Probably we will demonstrate maybe a few examples on this, and we have also some examples in the notes, but let me give you a simple example to finalize this. Okay, let's assume that we have a voltage source of 120 volts, angle 0, and an impedance here, okay, and another voltage source here. Let's say we have here 40 or 50 ohms, angle 30 degrees, ohms, and this is E1. And let's assume that E2 is 90 volts, angle also 0. Okay? Now, based on this, we can calculate what is I. I is equal E1 minus E2 divided by 50 angle 30. So it will be 120 angle 0 minus 90 angle 0 divided by 50 angle 30. Then here we get 30 angle 0 divided by 50 angle 30. So you get 3 over 5, which is 3 over 5.6 angle minus 30 degrees. Okay, so this is amps. So this is the current. Now, S1 equal complex power supplied by E1 is equal E1 times I1. Okay? I supplied, and I1, we have calculated I1 equal I. If we look at I1, here is I1. Okay? So it's basically this one. So it is 120, okay, RMS value, times angle 0 times 0.6 angle minus 30, the conjugate of that. So it will be 120 angle 0 times 0.6. Conjugate of 0.6 minus 30 will give you plus 30 here. So here 6 times 12 is 72, right? 30 volt amps. So this is equal 72 cosine 30 plus J 72 sine 30. Okay? So this is P and this is Q. So this is positive and this is positive. Okay? So it means that E1 supplies P and Q. Okay? Now if we go to S2 equal E2 times I2. Now we go back to the circuit where this is E2 and this is I2. Now I2 is minus I. I2 this is equal to minus I. So this will be 90 angle 0, right? E2 is 90 angle 0 times minus I, minus 0.6, okay, 0.6 angle minus 30, angle minus 30, conjugate. So it is minus 90, okay, minus comes out. Say angle 0 here, 0.6 angle 30, because of the conjugate. So this will be 6 times 9 is minus, 6 times 9 is 54, right? Angle 30, okay? So this will be minus 54 cosine 30 minus J 54 sine 30. So here is negative and here also negative. i.e. source E2 absorbs both P and Q. Okay? The difference being absorbed in impedance Z2. Let's take this is Z2. This is, or Z equal what? 50 angle 30, right? Let's go back to it. Is it 50 or 40? 50 angle 30. Now this is 50 angle 30. And here in this 50 angle we have I here. And we have a voltage here. Let's say this is A and this is B, plus, minus, and this is VAB. Put it another way, I have a Z here equal 50 angle 30. And there is a current. Here A and this is B, this is point A, this is point B, and there is current supplied here I, and here VAB. Okay? So we call this S in Z is equal VAB I conjugate. Now VAB, this VAB equal E1 minus E2, okay? And I is equal I, okay? So that's the difference, VA minus VB. Now, if we look at VAB equals Z times I, right? So what we get is Z equal VAB, which is Z times I conjugate. Here will be Z times I squared absolute. Okay, so we can calculate that. Z equals Z times I squared. So Z will be what? 50, okay, angle 30 times I squared absolute 0.6 squared. Okay, so this would be 0.6 times 0.636 times, or 6 times 0.6 is 3.6 times 50. You can calculate it using your computer or telephone. Let me just do it with you here. So what we have is 0.6 times 0.6 times 50 is equal 18. Okay, we have 18 here. We have 18 angle 30. Okay, so we have 18 cosine 30 plus j 18 sine 30. So here is q into z, and here p into z. You would find that, okay, you will find that E1 gives P1 equal, we have calculated that. Let's go back to it. S1, 72 cosine. 72 cosine 30. And E2 gives P2 equal minus 54, I think, minus 54. Minus 54 cosine 30. And Z takes PZ equal 18. Okay, cosine 30. We take this 18 cosine 30 and 54 plus 54 cosine 30, you will get what? 272 cosine 30. Okay, so this is P1, this is P1, this is PZ, and this is P2, which means that source E1 gives P1, which is given to source E2 and C2. So this is 72 cosine 30, and here E2, which goes to 854 cosine 30, and here 18 cosine 30. So 72 cosine 30 is the total supplied power from source 1. Part of it will go to the impedance, absorbed in the impedance, and the other part will go to source 2. So source 2 is negative. It means source 2 supplies negative power, which means in other words, it means that it takes positive power. Okay, same for also Q. E1 supplies Q1. Okay, part of it will go to E2, and part of it will go to Z. Here is 72 sine 30, 54 sine 30, and here is 18 sine 30. Okay, it's the same. So the 72 sine 30 is supplied by source 1, part of it will go to source 2, and the other part will go to the impedance. I want you to keep in mind all these things, okay? Read please the notes and the examples, and keep in mind all these things. And in Ramadan, inshallah, I will try to make the final video regarding transformers and three-phase circuits. Now you are equipped. You read the notes, understand the videos, you are equipped with the fundamentals of both DC and AC circuits and their theorems. Okay? Okay. We'll make other quizzes or tests also for you. Now we have made one basic test and another one on series parallel. We'll make another one probably on one or two on both methods and theorems on DC circuits. Well, in Ramadan, we'll move to AC circuits and give you a few tests, 2 or 3 tests, okay? So good luck and talk to you again maybe next week in Ramadan, okay? Thank you.